In this video, I will show you how to perform a multiple linear regression model in Excel and how to interpret the output. But the first thing we need to do is to double check if there exists a relationship between the variables. So that will take us to correlation before we proceed to the regression analysis, where we need to fit the multiple linear regression model, estimate the parameters of the model, the unknown model parameters. And thereafter, we could also proceed for further statistical inference, such as hypothesis testing, to investigate if the predictor variables or the explanatory variables, also called the independent variables, are contributing to the model. But if they are not contributing, that is, they are insignificant, then of course they could be removed. We'll consider them as nuisance components. All right, moving on now, we go to the data set. So we have this data set. The first column, column A, gives the count observations. So here, count 1, 2, 3, 4, and so on till the last value, where we have 111. So altogether, we have 111 observations for each of the variables. And of course, we could see many variables. Y is our response variable or the dependent variable. Then we also have X1, X2, X3, X4, X5, X6, X7. All of this makes up a vector of the independent or explanatory variable. So to do this analysis is quite easy, but like I said, we want to first of all double check in terms of the relationship. Does any relationship exist between Y and X1, Y and X2, Y and X3, and so on till X7? And what kind of relationship? Is it a strong positive correlation or a weak positive correlation? Is it a strong negative correlation or a weak negative correlation between these variables? So we just want to double check. And if there does not exist any relationship, then of course we do not need to proceed to fit the regression model. Otherwise, we will obtain what we call spurious regression. All right, so we want to go for the correlation analysis first. So at the top icon, if we click on data, then we have a drop-down menu. You move down to the top right, where we have data analysis package. And then you go to correlation, because we want to deal with correlation first. So from this drop-down menu for data analysis, in the analysis tools, we click on correlation, and then we tell Excel, okay. And what you want to do, you have to impute all this, excluding the count, because that's not part of the analysis. It just shows at point 1, point 2, point 3 different points with which we have these values. So we highlight from Y to X7, from the first to the last observation. And then the next thing we want to do, we want to also take this option, group by. Is it by columns or by rows? Of course, they are grouped by columns. So we're happy with the column. It's automatically done, and we're happy with that. So the next thing, of course, we need to tick this box because labels represent the first row. And in this case, is the variable names. So like you could see here, we have the variable names, all the variable names. So that's why we leave that. That's fine. Then the output range, where do you want it to be? It could be anywhere. You could go up if you want. But in this case, I want it anywhere at all. Let's assume that we go up now. Okay, for these that I've explained earlier, labels in first row, you could see the first row. The first row, row 1 here, represent the variable name. So that's the reason why I tick this. But if row 1 do not represent variable name, but rather the observations, then I don't need to tick this. I will untick. Otherwise, the first information will be lost because Excel will regard this first row as variable names. But in this case, that is useful because I actually use the first row to represent the variable names. Hence, we tick the box, labels in first row. That's fine. So it's good to understand this when performing this kind of analysis. Now, where do you want the result to be? Okay, I want it to be elsewhere. Let me scroll down. I want my result to be down, 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 somewhere here, for instance. So I proceed, and Excel will give me the result. So you could see the correlation matrix. We could color this if we're happy with that. Could use any color of our choice. Could color it. Again, if we want to make it in matrix form, that's fine. Again, if you want to also put it in tabular form where you could format it, that's also fine, whichever way. But like you could see here, you notice that the correlation of a variable to itself is 1. So it's a perfect positive correlation. Correlation of y to y is 1, x1 to x1 is 1, and so on till x7 to x7 is also 1. But let's see, x1 and y is a positive correlation. You could see here, 0.64764. x2 to y is negative. So that's a negative correlation. x3 to y is positive correlation. x4 to y is also positive. x5 to y is positive. x6 to y is positive. x7 to y is negative. So x2 and x7 have negative correlation with y, while the rest variables have positive correlation with y. Then again, you could also check the strength of the relationship. Is it a strong or a weak correlation, and interpret accordingly. But of course, our aim is just to establish whether there exists a relationship or no relationship at all between the variables. And of course, we could see clearly from the statistical evidence that there exists a relationship between the variables. So the next task is for us to fit the multiple linear regression model. So again, we go back to data at the top icon, and then at the top right, we will see data analysis, top right-hand side. Then we proceed from the drop-down menu, we will see regression. So click on the regression, then you proceed to say, okay. Then what we need to do now is to impute Y range, which has to do with the response or dependent variable Y. So impute the range of values for Y. Now we have the range of values for Y. Next is the values for X. And in this case, the X takes the form of a vector or a matrix. So this is a vector of independent or explanatory variables. So we have from X1 to X7, all of these. That's fine. Then again, labels, that's fine, because you could see that the first row represent variable names. And that's why we take the labels to tell Excel that the first row of the data in this Excel spreadsheet actually represent the variable names. The next, again, you look at constant is 0. If you tick this, then you're telling Excel to exclude the constant or the intercept. Otherwise, untick it. And of course, I have to untick because I also need the intercept, the vertical intercept or the constant term also in my multiple linear regression model. Then the confidence level, I'm also happy with 95% confidence level. But if you're not happy with this, you could tick here and then you could change if you want. For instance, if you have 99, you could have 90, whichever. But by default is 95% confidence level. So that's fine. And the output options, where do you really want this to be? You will need to also tell Excel, let's assume you're happy that the result should be somewhere here. Then you tell Excel to publish the output here. Again, You could also see residuals, standardized residuals, residual plots, line fit plots. Then, of course, in terms of normal probability, we could double check for normal probability plots. In this case, to see whether the data set follow normal distribution or not. But of course, we're not concerned with being normally or normally distributed. In this context, we're just looking at fitting the model. So we assume that all assumptions of the model are met. So now we could go ahead to tell Excel, okay, and the job is perfectly done for us. You could shift the cells in order for you to see them more clearly. That's absolutely fine. You could shift this also. You see the model coefficients. You could see the standard error. You could see the T statistics. You could see all of these. All right, so this is what we've got. Let me again color this first part, so that we can interpret them accordingly. Let's assume here I use orange color, and then for the ANOVA, we use a different color. If I'm happy with, okay, let me use other ones so it could look clearly. Let me assume that I use light green, and then for the model coefficients, I could use yellow. So we could see the result. This is a summary output from the Excel. Now this is the multiple R, which you could see now. This is multiple R. Then we have R squared. That is the coefficient of determination. This gives a kind of measure in terms of the variation in the independent variable. So the R square value, which is a coefficient of determination, actually gives us the total percentage of variation explained by the model. So to what extent does the change in the response variable or the changes in the explanatory variables affect the changes in the response variable? So if there are changes in X1, X2, X3, X4, X5, X6, X7, to what extent will Y respond to the change? If Y does not respond to the change at all, then of course, we could have a value very close to 0. But where we have a value from 50% and above, then it shows that it is a good fit. Where you have a high value, for instance, from 70% and above, that's good. Then, of course, here we could even see above 80, we have about 82% of total variability. So this is the proportion that has been explained by the model. So we could say that it's actually a good fit in terms of statistical interpretation. So it is a good fit. The changes in X1, X2, X3, X4, X5, X6, X7 actually affect the change in Y. So in that case, this actually accounts for the percentage of variability or total variation that has been explained by the multiple linear regression model. Of course, you could see the observations, you could see the standard error, the adjusted R square also is very close to the R square. Then the ANOVA, this gives the overall performance of the model. The overall performance of the model. So we have significance F. There you could see the F. This is the F calculated. And of course, with the significant p-value, which you could see here, 2.75337 times 10 raised to the power minus 33. This is approximately 0.0000 to 4 decimal places. So it means that it is highly significant. It is highly significant, and we could also say that there is a strong statistically significant evidence that the overall performance of the model is okay. All right. We could also see the intercept. Of course, we included the intercept. So this is the intercept term. So if you want to put it properly, we could say y, this y is equal to, I could put it here if I want. We'll take it again. Could say y is equal to this intercept. This value, which is 20.3496 to 4 decimal places, plus the coefficient of x1 times x1. You could see the coefficients. These are the standard error. I could shift it again so we could see it clearly. Let me shift this. So we got a standard error. The T star, this is the test statistic, or the T calculated. Then, of course, you have the P values. So the next is 0.086. Okay, let's add more values. 59. So 0.0859 to 4 decimal places times x1. Then plus what follows? We have the next value. That is the coefficient here. So the coefficient of x2, we could see this value is 4.06. So this means you have about 0.000 up to 7 zeros before the 406134. But we could just put it in the way it appears. That is 4.0613. E raised to power, that is times 10 raised to power 07. So you have this times x2 plus for x3, the coefficient of x3 is negative. So plus times minus is minus. So what we have is minus 0.319 times x3. Next is x4. Coefficient of x4 is positive, which is this. So we have, or if you're happy, you could also include it here. We'll say plus. What next? 0.5522 times x4 plus what follows? The coefficient of x5, 0.2386 times x5 plus the next is x6. Coefficient of x6 is positive, 0.0015. Because if we approximate 9 is 1. 1 plus 4 is 5. So 0.0015 times x6. And finally, x7. So for the x7, we will have the coefficient is negative. So plus times minus will be minus. And so we have minus 0.0861. Approximate 5 is 1. 1 plus 0 is 1. So times x7. Of course, we're supposed to include the error term E, but we don't need to do this. When you estimate the parameters of the model, you assume that the expectation of the error term E is equal to 0 as part of the assumption. So the mean of the error term is 0 because we assume that the error term is distributed with 0 mean and constant variance. So the error term is normally distributed with mean 0. So the expected value of the error is 0, and also the variance is the constant variance. So because of that assumption, we can now remove this. So we'll leave this as our result. Let's see what we've got. So we've got all of this. Let's highlight all. Okay. I could bring this back if we want. Let me see if I could put it here. If there is space now. So what we've got is this. Y is equals to 20.3496, which is the intercept or the constant term, plus, that is times x1, so you multiply it by x1, plus 4.0613e raised to power 07 times x2 minus 0.3190 times x3 plus 0.5522 times x4 plus 2386 times x5 plus 0.0015 times x6 minus 0.0861 times x7. Of course, we want to double check for significance. Beginning with the constant term, you could see the p-value is by far less than 0.05. So the intercept or the constant term is statistically significant. Moving on to x1. x1 has a p-value of 0.000137, which again is by far less than 0.005. So x1 is statistically significant. Moving on to x2, you could see the p-value 0.5200793. So clearly, this value, the p-value, sorry, I'm interpreting something else. 0.604124 rather. So that is the p-value column here. So you could see that the corresponding p-value to x2 is 0.604124. So this indicates that x2 is statistically insignificant. It is not significant. And that is why you are seeing this kind of value you have here. It's similar to just having a 0 value from what you have here. Okay, let me do something here. Assuming I leave like this first, then come back here. I could add plus here. And then I could copy all of these. Okay. All right. So I put it this way. So you can now see that we have the coefficient of x2 is a value that is approximately 0, because you got 0.0000046113, which is approximately 0. Because this means this figure here, 4.0613 times 10 raised to the power minus 7, which is approximately 0 if you round it to 4 decimal places. So you see that this will be 0. This. So we have 0 value here. And that is why it is insignificant. It does not contribute to the model. So it can be removed. And of course, when you remove a variable that is insignificant in a model, it could even go a long way to improve the predictive task of the resulting model, if you include only the significant predictors. Moving on to the next one, X-ray. X-ray has a p-value of 0.00599. Again, is by far less than 0.05, so it is statistically significant. If we move on to X4, we have p-value 0.000497 is statistically significant. So long as the p-value is less than 0.05, it is statistically significant. But where it is greater than 0.05, then it is statistically insignificant or not significant if you are testing at 5% significance level. And of course, for a standard test of hypothesis, we normally use 1% or 5%. So you could say that for those that are significant at 5%, they are also significant at 1% from this analysis. X5 has a p-value that is approximately 0.0000, which is highly significant. X6 also has a p-value that is highly significant. And X7 have a p-value that is highly significant. Even though X7 and X3 have negative correlation with the response variable Y, they are statistically significant. They could affect negatively, but they are contributing to the overall performance of the model in this case. So if we are to remove an insignificant variable here, then clearly we will remove this X2 that does not contribute anything to the model, and the rest variable will remain. So we could see clearly from this analysis. We also have the lower 95% and the upper 95% confidence interval. So this is given a kind of additional statistical analysis, and in particular further inferential statistics about estimation of the parameter. Yes, from this data set, we have a sample, but if you go to the entire population, what the confidence interval is telling us is that due to, for instance, limited resources, time, money, cost involved, and all of that, that we have few observations as a sample, a random sample of observations out of the entire population, that the estimator is unbiased. So in this case, what you estimated as the specific value, we also make a provision for an interval such that the true population value will contain this value that has been estimated. So we are 95% confident that this interval contains the true population value. For instance, the parameters that we have estimated. So even though we may not be 100% sure in the case of carrying out a research or doing this kind of analysis where you are not 100% confident, you allow some level of error, then the interval here is giving us the assurance the confidence that the true population value will lie between this lower and the upper bound of the 95% confidence interval. So here ends the video regarding the analysis of a multiple linear regression in Excel. We've done the correlation, and we've established that there exists relationship between the variables, positive and in some cases negative correlation. Also, we fit the model and we proceed to estimate the parameters using the Excel. And then we carry out hypothesis testing. And of course, in terms of hypothesis testing, this is what we are saying. A HO is saying, that is the null hypothesis, is saying that all estimates or parameters are 0. And then we have versus. The alternative hypothesis, which is H1, is saying that not all parameters or model coefficient estimates are 0. So at least one of them will not be 0. There is no way we could just say that all the parameters of the models will be estimated to be 0. So that is the argument here in this hypothesis. Could put it in red. So you could see the null hypothesis is saying that all estimates or parameters are 0. So beta 0, beta 1, beta 2, beta 3, beta 4, and so on till beta 6 and beta 7 are all 0. While the alternative hypothesis is saying that not all the parameters are 0. 1 could be 0, 2 could be 0, but not all are 0. And of course, we could see clearly that not all the parameters of the model are 0. It is the coefficient of x2 that is 0. The rest of them are not 0. But this has been justified from the statistical evidence and not to be said verbally. Thank you so much for your attention, and thanks for watching this video. Bye.